Good evening and welcome to live session 5, sorry 9, live session 9. Until now we have uh, seen many of the name reaction and total synthesis and continuing the trend. So I am going to start with the assignment with some assignment problems and followed by discussion of some of your problems. So let's start with today's first problem. So this is the first problem, and here you can see this is the retrosynthetic arrow, and they are asking about what particular kind of transformation can lead to from this starting material to this target molecule. So this kind of system, I think now all of you are well acquainted and can easily solve this kind of problems. So when you see this kind of thing, so here you can easily thought of one migration have to be happen from here to here. Otherwise, how this butyl group could be forming from here. So if we do that and shift one of the carbon one of the methyl group over here, so there would be positive charge and which would be can be neutralized by keto formation. So this particular type of rearrangement is one to shift you can think of. So it is easily a pinacolon type rearrangement. So let's look at. So here if we apply acidic condition, one of the hydroxy group would be protonated and it would make one of the hydroxy group good living group. So this kind of species would be forming, and due to its very high living aptitude, so this would tend to eliminate and form one and try to form one carbocation over here. So you can think of in that way, or if we consider the concerted way, so directly we can push the arrow like this and do this particular one to shift, and which would lead to formation of here keto group and here the tarbutyl group, so which is nothing but our target molecule. So that's how you can easily solve this kind of problems, and so A should be the right answer. So Eisenhower Tanabe fragmentation, so if I want to discuss that, so I have a little example for that. So this is actually Eisenhower Tanabe, this particular fragmentation reaction. So I am going to discuss all of these three also. So at first I am discussing this zone. So this is actually Eisenhower Tanabe. So this upper one. This Eisenhower Tanabe. So for that, our the reagent of the, you can see the starting material would be this kind of compound. So which is nothing but, here you can see one epoxide is there, which is in the position of alpha beta of a keto or carbonyl compound. So how you can make this kind of compound? So I think all of you know that, because many times in the previous classes I have discussed. So let's say this kind of alpha beta unsaturated carbonyl compounds can be easily made. You can also form aldol condensation type reaction. So from here to here, how we can do that? So for this kind of regioselective epoxidation reaction, we need this particular condition H2O2 and NaOH, and we can easily generate the epoxide over toward this center. So for mechanism purpose, so H2O2 one of the proton first can be abstracted by the basic treatment of NOE. So this nucleophile can attack over here. As you know, this is the electrophilic center, and after that, and as this is attacking, so here uh, this carbon would have higher electron density, or you can think of an delta negative. So this can act as nucleophile. So after this kind of thing, this particular epoxide can be formed. So from this starting material one, if we treat this type of hydrogen hydride type uh, this particular sulfur based reagent, at first what would be happening, at first condensation reaction would be occurring, because this NH2 is nucleophilic in nature. Due to alpha effect, you can say it have more nucleophilic tendency, so that's how this particular 1-2 attack is happening, and followed by water elimination would lead to this formation of this hydrogen type moiety. So from here, so let's say here you have base, or without base this can also occur anyway. So this particular hydrogen is acidic. This is an acidic proton. So base can easily abstract this, followed by this particular nitrogen double bond formation, and followed by this epoxide ring opening. So this particular cascade thing would be occurring in this type of intermediate, which would lead to formation of intermediate 4. From here, what is happening? So here you can see when this kind of N double bond N is there, and this is a very good living group. And so when this kind of species is formed, so the molecular intermediate always try to remove nitrogen from the system to get stabilized. So as nitrogen double bond is already there, so what we need, one extra bond. So how it is doing that? So here you can see the hydroxy group. This particular proton is doing actually the electron is actually pushing electron, followed by proton elimination. So when the electron is pushing hyper here, and this particular carbon bond is breaking, and when it broke, it have to come here, and followed by nitrogen elimination, and this particular uh, this sulfur based acid is removed. So these two would be the byproduct. The nitrogen, it would eliminate as gas, and this particular acid would be removed. And so you can see in our why it is an Eisenmuller-Tanabe fragmentation. So you can see in this particular alpha beta, this particular bond, carbon bond is breaking in the reaction sequence. So this particular bond is broke, which, so one part we are generated the one alkyne moiety, which is 6, and another part we have generated an aldehyde moiety. So that's how the fragmentation work, and this particular 6 and 7 compound is formed. So this particular reaction is known as Eisenmuller-Tanabe reaction, Tanabe fragmentation, you can say. So we have discussed what is the Eisenmuller-Tanabe fragmentation. So next is boron nitride ester photolysis. I hope you guys know, but let me discuss a bit. So this is actually nitride, and as it is ONO, so that's why it is called nitride ester. So this particular for this particular group ONO, so NO is nitride, and in the as nitrogen oxygen bond is there, so we are comparing with esters and calling it nitride ester. So when we treat this kind of compounds, we shine light or so at first one homolytic cleavage between nitrogen and oxygen bond occurs, and it generates two radicals. So this particular NO dot and O dot. Now what happens? So here you can, if we name, so alpha, beta, gamma, delta. So for this kind of button nitrate reaction, always we need to have an delta hydrogen. So this O dot can abstract this particular hydrogen from this carbon center, and so the question is, why not other hydrogens? Why only the delta hydrogen tend to abstracted by this water? So the reason is simple, because if we thought of the transition state, you can easily think of an six-member cyclic transition state. So that's why the stability of this particular transition state would be much more rather than other possibilities. So that's why this delta hydrogen is abstracted. So now the recombination is there. Here the C dot is generated, and in the system we already have NO dot. So that to just form a bond, two radicals, you can call it as an recombination, which will lead to formation of this particular intermediate. So here you can see both these two are just tautomerization or tautomers. So this particular compound can exist in two forms. One is in purely NO, and one is NOH. Simple tautomerization, stabilization, or this particular two forms can exist like that. So this is Barton ester photolysis, and for the mean wall rearrangement, it have quite similarity with semi-pinnacle rearrangement. So let me discuss first the mean wall rearrangement. So at first, for simplicity, let's think of a system like this only. Here let's see, we have R1 and R3, R4. So when we treat this particular compound with Lewis acid, at first what would be happening? Lewis acid and uh, this particular oxygen at first from this kind of interaction would be there, or this particular oxygen and Lewis acid bond would be formed. So Lewis acid here might be LCl3 types or BF3 types. There are many Lewis acid that can be used over here. So now, so some of you maybe raised your hand. So if you have any question, please ask. Okay, so if there are no questions, so let us continue that. So when this Lewis acid particular this type of thing forms, then system would try to break one of the bonds. So A bond or B bond. So one of these two bonds can be broken. So how the system would decide which bond to break? So it can easily be uh, explained by the stability of carbocation. So let's say here we have not R. Let's say for our this case R4 equal to proton. So when if R4 equal to proton and all R3, R1, R2 and R3, let's say, are simple CH3. So when a bond will be breaking, so particular this bond would break, so we would generate this particular carbocation, and here we have this particular complexation, and here it is. So let me write methyl, and one hydrogen is there. If a bond is broken, this particular intermediate would be formed. If B bond would be broken, so we would generate this particular carbocation. So between these two, you can easily see this is an 3 degree carbocation, and this is secondary 2 degree. So among these two, as this one is more stable than that, so breaking of B bond would not be preferred by the particular this molecule, and A bond breaking of A bond would be preferred. So after that, what would be happening? So it is in this kind of form. So now this kind of migration can easily be happening, and particular this kind of thing is formed. So it is quite similar with pinnacle type rearrangement actually, but there is some difference. So here you can see the differentiation between them. So let's say these two are same compound. So for the first case, what we have done, we have done just H plus T for the pinnacle type rearrangement. So at first this particular protonation would be occurring in this particular oxygen center, and followed this OX. So uh, so X is nothing but a salt, you can think of ONA type. This kind of thing is there. So now this electron density can easily be pushed like this, and R5 would directly attack this particular center, followed by this epoxide ring opening. So which would lead to formation of this kind of protein. And when we treat this particular molecule in Miniwald rearrangement type reaction condition, so let's say in Lewis acid we have treated in this particular same compound, then what would be happening? At first this particular bond is forming, and R1 would be shifting due to stability of this particular carbocation comparing to this. So this would lead to formation of this. So here you can see two regioisomers can be formed, just differing the condition a little bit. Semipinnacle rearrangement can lead to this, and Miniwald rearrangement would lead to this particular compound. So that's how these two rearrangements are quite related, and sometime you can expect the mixture of products, and so in the reaction condition you may get both of them in same amount, or one of the would be major and one of the can be minor. So this kind of rearrangement have uh, lower selectivity issues, but these two are important thing that you can remember. So for the second problem, here again, here we have a retrosynthetic arrow. So this is our starting material, and this is target molecule, and they are asking what kind of transformation can lead this to this target molecule. So if we do the retro arrow or retro disconnection, we can do this. So if we do that, we can generate this followed by one synthon, that would be this kind of synthon we are going to need. So how we can have this kind of synthon? They are and we need a double bond also. So this kind of synthon is can be easily accessible by Vedic salts. So uh, this kind of Vedic reagent can easily be reacted with this kind of aldehyde molecule to form this particular this molecule. So let's do the mechanism over here. So at first normal 1-2 addition would be happening, which would lead to formation of this particular this particular intermediate. So this full membering be forming over here, and after After that, phosphine oxide would be removed, and which will lead to formation of this particular olefin compound. So that's how you can solve this, and the reaction, the right answer should be Wittig reaction. And as you can see, this particular molecule is symmetric one, no issues of EZ selectivity. That's why here any of any side methyl, that would be the same compound. But if let's say we have then methyl, then if we treat the same Wittig salt, what would be the product? The methyl would be this side or this side. So for that we have in the previous classes I have multiple times I have discussed. So this particular Wittigs, as they are unstable Wittigs, so they are not stabilized by the resonance with, let's say, if we have keto functionality over here and versus here we have only alkyl group. So here the carbanion is purely located over here, it cannot be delocalized, so this is unstable Wittig. So unstable Wittig always give Z stereochemistry, and stable Wittig always give E stereochemistry or E geometry. So if this compound is there, then the product would be Z1, sorry, no, not benzene ring. So the product would be this kind of thing. Although the molecule, the stability of the molecule would be less, but still the major amount of the product would be this. As unstable Wittig go through a it is quite selective, and it go to a kinetic stable product. So it is an KCP condition. For the unstable Wittig, it is always give the KCP product, and stabilized Wittig always give TCP or thermodynamically controlled product. So that's how you can do this kind of problems. And for the Bart's reduction, I hope all of you know that. So let me clean this. So for the Bart's reduction, so let's say we have an benzene ring, and here our group can be electron withdrawing or electron donating. So EWG or ETG. So for the EWG, electron withdrawing case, here for the Bart's reduction, condition is sodium ammonia, and the particular electron can attack this particular center or this particular center. So for the electron withdrawing cases, this particular center would be more electropositive. That's why attack would be occurring over here, and which will lead to form this kind of 1,4 reduction. It would lead to, and the product would be like this if the R group is electron withdrawing, and if electron donating group is there, then most electron positive center would be this meta center, and then the arrow pushing would be like this, and then we would generate uh, this kind of reduced product. So that's the Bart's reduction condition. And for a Tchaikovsky, I have discussed earlier, but for brief overview I am giving now. So for the Korsakovsky case, let's say this is our starting material. So here also we can use two ylides, right? So let's say at first we are using, so here the ylides are sulfur based actually. So let's say this this is one of the halides, and another halide is this particular halide. So again here we have a case of stable and unstable halide. It is unstable due to it cannot be delocalized, and it is stable due to it can be resonance conjugation with this sulfur oxygen isomer. So now with the Hartsoft HSAB principle, we can easily solve this kind of problem. So this particular center is softer, and this particular center is hard. Why is that? Because of the electronics. You can easily think of that if we do this resonance here, the positive charge that would be generating due to it have long distance from the this particular keto group, and if this particular positive charge we generate, it would be directly connected to an electron or electronic highly electronegative atom. So that is why this is a hard center and this is a soft center. And similarly, this is also softer due to it is in resonance, and this is a hard center compared to this particular compound due to it is a located or non-conjugated system. And this is by the Hartsoft rule, but with homolumo again the same thing can be discussed. So it is more stabilized, and this particular pi star would also be more in the lower energy compared to this keto. So that's why the energy matching between this nucleophile and this pi star would be much lower, or energy gap would be lower compared to this. So that's how the selectivity came. And so when the stabilized we would be using this particular 1,4 attack would be happening. So if 1,4 happens, it would generate this particular compound. Now it is an electronegative system, or you can easily think of it is an enolate. So O minus can do the arrow pushing, and it can attack over this carbon center, can attack over here, and DMSO would be can be removed because it is a good living group. So when this happens, we would generate a 3-member ring over here, and the keto would be back like this. So if stabilized light we use, the product would be this. Now let's see if this particular unstable light is. So here we can expect an 1,2 attack. So when 1,2 attack will be happening, so here O minus we generated, and here carbon and SME2 plus. Again you can see this is a good living group, so this is a good nucleophile. O minus can attack like this, and the double bond is intact. And uh, can you please mute yeah. So if that happens, oh, sorry, here we would generate an epoxide because this carbon is there, this epoxide is generated, and the olefin system or double bond would be intact. So that's how we can easily control the products or regioselectivity of this compound. So if we want to regioselectively react with the carbon-carbon double bond, and we want to remain, or we want to keep this particular C double bond, we can use this kind of stability lights, which will lead to this. Here you can see the keto group is unreacted, and if we want to selectively react or form an epoxide over here and want to uh, keep this particular double bond intact, we can use this particular hard nucleophile, which will lead to formation of this compound. So these two conditions are for Korechak-Kopsky type reaction, and that's how we can control things. For the Starrett oxidation, it is well known, but let me discuss a little. So Starrett oxidation and this particular thing, the chromium trioxide and two pyridine molecules, and this particular aggregate is known as Starrett reagent, and this is used for oxidation reaction. So let's say here we have a secondary or secondary here we have this particular primary alcohol. Not secondary one. If secondary alcohol is there, we would generate one keto compound. So this particular primary alcohol, at first the chromium is the electrophilic center, and this oxygen can from this chromium oxide bond, and which would lead to formation of this kind of intermediate. And in the system, the pyridine is used, and it can be used as solvent also. So pyridine's nitrogen would show its basic character, and it would abstract one of the proton, and it would then it would abstract one of the proton, and here the oxygen would be neutralized. So which would lead to formation of this kind of compounds. Now this O minus can easily abstract this proton, followed by this carbon oxygen bond formation and oxygen chromium bond breaking. So this is a classic mechanism for any kind of oxidation reaction. One CH bond would be broken, and carbon oxygen bond would be formed, and oxygen chromium or oxygen sulfur, which species we are using for oxidation, that would be broken. So this is a generalized mechanism. For this oxidation, it is no exception. So this is a Starrett oxidation. So that's all for the problem number 2. So I have discussed all 4. What are those, and you can easily solve this kind of things. So now coming to next. So here also you can see this is the starting material and target molecule. So here to here you can again you can see the first problem itself. I am discussing the pinnacle type rearrangement, and here also the same case. So for meanwhile, what I have told that it is for epoxides. For epoxides, if we have epoxides, then only meanwhile rearrangement we can think of. But here you can see no epoxide is there. To hydroxy one to dihydroxy compound. So pinnacle type rearrangement would be occurring. So let's say we have started the reaction or we treated this molecule with acidic or proton H plus. So one of the hydroxy group would be protonated. So let's say at first this particular oxygen got protonated. So thing would be like this. Now the one to shift this particular this. So this would generate. So this target molecule, which is like this. So this would be the product, and the right answer would be B. But let's see why this particular oxygen is not protonated. So if this one is protonated, OH2 plus, and then again one to shift would be like this, which would generate a 6,3, this kind of spiral cycle. So between these 5,4 and 6,3, so system always prefer this kind of thing. So that's one of the reason why this is happening, and there is also another reason. So if we do not consider in this concerted way, rather we think of an carbocation formation, then also we can easily discuss this thing. So let's say it is not concerted and carbocation formation is happening first. Then let's see what is. So if carbocation formation is over there, so it's a 3-degree thing, this particular carbocation versus this particular carbocation. So which one is more stable? So we can easily discuss the stability of these two, between these two, using the nature of this type of cyclopropane rings. So we all know these cyclopropane rings are not this particular carbon is not like normal sp3 carbon, as due to the very strained nature, so its angle is only 60 degree. But we all know the for the sp3 thing it need to be 108, around that thing. So due to the huge strain of this type of cyclopropane system, so the the character of this particular carbon is much more higher than sp3 one. So it's just lesser than sp2 but always greater than sp3. So if we consider hybridization, we can think of like this. So the hybridization of this particular carbon is not sp3, it's quite close to sp2. So for that, it have you can just consider the stabilization effect of one vinyl type group. Let's say if we have vinyl type group over here, then this particular resonance stabilization over there is can be easily think of due to hybridization of this particular carbon is sp2. So as this carbon is quite close to sp2, this particular stabilization over there due to its availability of the p orbitals, this interaction is there. So that's how this particular carbocation is stabilized with the help of p orbitals or Morris character of this particular carbon atom. But for this case, you can see there is nothing like that is there, because it is a 5-member ring. So the strain compared to 3-member ring is very low. Here it's a stable system for the 5-member ring, and no such stabilization over there is stabilization is there. And moreover, S character is higher in this carbon. So you all know the positive charge on highly S character carbon is very much unstable, because it's these three examples. So this particular carbocation, this particular carbocation, and this carbocation, which is more stable, this, then this, then this. So compared how this is described, because of the S character, so it is sp3. So S character is less, it is sp2, and it is sp. So S character is increasing and the stability of the carbocation is decreasing. So similarly, S character of this particular carbon and this particular carbon, so S character here is higher, so carbocation formation stability is lower. So that's how you can easily describe the carbocation stability. So that's why this particular thing is unstable compared to this particular intermediate, and here to and here just want to shift to this particular one. So that's how the selectivity came, in which side the carbocation would be formed. So that's how the pinnacle rearrangement would happen. Now coming to Wagner rearrangement. So it is nothing but that Wagner-Melvin rearrangement. So all of us are reading it since probably school days. So it's a simple example of the this Wagner-Melvin type rearrangement. So if H plus is treated in this particular molecule, this This is also a classic example for this kind of rearrangement thing. So at first this particular 3-degree cation would be forming because here this particular thing is happening, then this. Now just the series of 1 to shift would be happening. So first 1 to shift would lead to formation of this particular 4-member ring, and we all know the stability of 4-member compared to 3-member is higher, and that's why this rearrangement is happening. So now here as we have broken bond, so here we have a carbocation like this. So now the same thing would be happening here. Again we have generated carbocation, same. So series of 1 plus 2 would be happening over here. So multiple arrow I am writing 1 to shift. So shift after series of 1 to shift. So all. So let me write the last intermediate. So last intermediate would be here C is 3 and here the positive charge. So this would be our last intermediate, and here there is no possibility of elimination stabilization. So only thing can be happening. So in the system water is there. So that's how this particular alcohol is formed like this. Another interesting thing you can see that the respective two are always the in conformation. So if one of the 4-member ring would be above, another must be below due to the sp3 nature of this, because if one thing is there and another thing would always would be above, of course the repulsion is there. So that's how this empty arrangement is there, is controlled like this. So this is Wagner, and another thing is Cartier's rearrangement. So this is an example of Cartier's. So let's say how this is generated. So let's say we have at first we have a acid group carboxylic acid. If we treat with SOCl2, this kind of COCl we would be generating, and then if we treat it with sodium azide, we can generate this kind of CON3 or this particular molecule. Now in presence of heat, the nitrogen tend to remove, so that's when the rearrangement occurs actually. So here let me show this properly. So this is one of the azides resonating from. So just this is happening here, then carbonyl stabilization followed by this particular shift and formation of this elimination of this nitrogen thing in presence of heat. This and like that isocyanate type cyanide type thing is forming, NCO is forming like that, and from there so this is particularly Cartier's rearrangement azide to this NCO formation. So after that we can quite reactive compound. That's why we need to react this with, let's say here they have used water. So if this carbonic acid generated, then always this elimination of the carbon dioxide should be there, which would do the formation of an amine compound. So this is also an example of stepping down reaction, because we are removing one carbon from the system. So basically we are, if we have this particular acid, we can from here we can easily generate this. So here we are removing one CO2. So one carbon we are leaving. So that's why stepping down reaction, and it is also quite a good observation of how to convert one carboxyl group to one amine group. With the Cartesian rearrangement, we can easily achieve this kind of things. So this is Cartesian rearrangement. So again, for the third problem, I have discussed all four named reactions. Now coming to problem number 4. Again, very easy problem. And one thing, in between when I am discussing, if you have any question, please feel free to stop me at any point and ask. And let's see. So here they are asking to predict what can be the x. So here there are four options. So let's start with this. So this is just a strong base. So, and it is an active methylene type compound. So here there should be two, I think. So some mistake is there. So this particular thing is our reagent. So when we treat this particular compound with base, and this particular base, and here you can see two acidic protons are there. Because of the abstraction, the stabilization with this either carbonyl is very much, so that's why this particular protons are very much acidic. So we can generate this particular compound or this particular nucleophile. Now starting with A, so if we use AD, so this particular attack would be there. So now let's see. So this is a 1,4 addition because it is a soft nucleophile, so soft combination is there. So pH, carbanion is generated. This particular thing will be formed. Now after that, this carbanion can easily be quenched, or you can think of this particular acidic proton in situ it can take, or inactivity can take this. So either things are possible. So now carbanion is generated in this center due to the stability of this, and now this is also there. Sorry, pH is here, not there. So pH is the, that side. So pH is here. Now this carbanion again we do the 1,4 addition, so we should lead to formation of this thing. Here CO2. So here you can see it is actually matching with this, so the thing would be A. So now look at the other options also. So if this compound is there, then maximum thing would be happening is it can do 1,2 attack. So after that also, just after elimination of water, maximum thing you can be it can be formed is this kind of compound, right? So this is no use and matching with this. So this is not the case, and if BZ thing is there, so then the product would be this kind of thing, one four member thing, this kind of BZ this thing would be formed if this thing would be there. So that's why we can eliminate this also. And here there is no phenyl group, so the compound would be, if D is used, the formed product would be like this only. This should be formed if D is used. So that's how we can eliminate D also. So A is the right answer. Now this. So these particular reagents, so they are actually for the managed reaction, managed reagent, it will be forming. So formaldehyde plus this particular diethylamine, so this attack followed by water elimination. So these, so here proton would be removed, ETT. Now the this thing would be happening because proton is also removing, and combination of this would lead to removal of H2. So just like a condensation thing. So this particular species in the reaction mixture would be forming, and this is the reactive intermediate or reactive species for this type of managed reaction. So when we have this phenol moiety and this kind of reactive species, so as you can see the para position of this is blocked. So this only can attack with ortho position. So this particular thing will be forming first. So here it will be CH2, CH2 and this and this, and for aromatization it would be try to maintain this particular enol form. NET2 is there. Now the reaction would not stop in this particular condition because this particular species is very much available in the system. When this happens, the system is again more electronic, or this particular ring become more electronic. So again this attack is possible, and which would lead to formation of, so I am not showing keto form directly, enol form I am showing. So NET2, here also NET, and here methyl. So this thing would be our product. So Vmax is would be the product, and meta position cannot be activated here. Again meta cannot do the reaction because it is not electron rich center for this type of electron donating group benzene rings. There only one side they have reacted, so thus this reaction cannot be stopped in this particular form. It would always be forming this type of disubstitution reaction. So that's how it is. So we can eliminate. So next condition. So they are asking the best reaction condition. So this is a well-known reaction. We all know the reaction thing would be this. So uh, considering today's discussion, so for this, although this is the right answer, another possible reagent combination can be this particular thing. Just probably the previous or some 1-2 problems ago I have discussed. So this is classic example for this particular thing. So yeah, just in the second problem we have discussed the Fourier-Tchaikovsky reaction condition. So if we use this particular elites in this particular alpha beta unsaturated ketose, we can selectively make a 3-member ring or cyclopropane ring, and this keto can be remain intact. So this particular reaction condition. So that's why I have just connected these two. Here also that similar thing you can see the alpha beta unsaturated double bond, and this is remain intact. So how we can generate this triple bond? By this. And anyway, this is another reaction condition, but for these cases the SN and chromium, so compared to this the Zn copper couple, this particular thing is very much well known in the literature, which is Simon-Smith reaction. So this is the reaction mechanism. So zinc copper, this particular amalgam type thing, or just couple, or these two species can coexist like this, and with the CH2I2 at first, what is happened? One iodine is reacted with zinc, and this particular species is formed. So CH2I2 actually. So one of the I is reacted with zinc and form this kind of species. So Zni is positively, or a positive delta plus, and another is CH2I, which is this carbon is negative. So this particular, that's how this particular thing is coexisting, and this particular species is forming. So now this delta minus can attack this double bond, and again this delta minus can attack this this CH2 to remove the iodine. So let me write properly. So I, and here is sigma minus and Zn I plus. So this particular thing is there, and this is actually, this particular part is the active species for the Simmons. So this is our olefin moiety. So now this attack is there, and followed by this, which will lead to this. So this is nothing but carbene type reaction intermediate. You can just think of this CH2 dot dot the carbene. So the reaction mechanism is quite similar, just it is in ionic form. That's why this, here you can see this stabilization is there. The zinc carbon bond and zinc iodine. So here that's how the ionic interaction is there. That's why this I have written like sigma plus and sigma minus, or but the main thing is the carbene generation. You can correlate this, how the carbene reacts is also react like that, but here it is in ionic interaction thing is there. So that's how the and Zni2 would be our pipe. So so here you can see here we have chiral centers. So when we do the reaction, there would be no phase selectivity. So let's see, say we have this particular olefin. So the formation of triple bond can be from this side or this side. So let's say this is high phase and this is D phase. So both are equally accessible by this reagent. So when we form this particular thing, it would be plus minus. The racemic thing we are always be generating. So now that's why people want to make it a asymmetric thing. So we need to have a strategy for any kind of this particular reaction where the reaction is either positive or negative. How we can control this thing? So how we can make one of the enantiomer as major. that's why there are many reports, but here one of the easier thing that just I have incorporated. So here you can see one chiral molecule. So it is a cyclohexane, and one of the is above. So anti-conformation is there. So let's see the RS. So one, uh, two, three. So add R, and here it is again 1, 2, 3 aces is there. So as hydrogen, so RR. So particular this enantiomer RR, and this particular ligand we can use. So if it is used at first, what it would do. So with zinc it would coordinate. So here you can see the model for the chiral reaction. So here is the zinc, and these particular two amine centers have attached with this particular zinc compound, and here you can see one hydroxy group is there, which is the anchor, which plays the anchor role, how to hold this molecule and the zinc. So that's why this OH is important. So now this OH is attacked or make the coordination bonds with zinc. So now after this particular intermediate or this bond formation, the oxygen zinc bond is fixed. Now the Zn do the same thing, this particular arrival of the CH2 thing. So the same intermediate thing here it is written. So this particular complex intermediate or transition state we would say would be forming. So when it is there, you can see. So due to the chiral nature of this particular ligand, one of the phase would be more accessible compared to other one. So that's why one of the phase would be reacting and another phase would be reluctant to react. That's why it come only from above the phase. Of course, the from below the phase some thing would be coming, and so that's why we need to make this ligand more bulkier. So optimization are there. So this is just a starting point of this type of chiral reaction. So that's why they have achieved up to 70 or 68% enantiomeric excess and 75%. So that's how the chiral. This is just a chiral version of Simon-Smith reaction. So this particular transition state you can just think and easily understand why one of the phase is reacting and other is not. So for this case it is easier. No chiral version is there. Just zinc copper couple and CH2I2 in THL media. So this particular reaction would be happening, and this 3-member ring would be. So the answer would be A. So coming to problem number 7. So this particular combination just we have done. So it would generate a species like this. So which is nothing but managed reaction intermediate, and so it is an example of so managed reaction intermediate. So easily we can solve by looking at the reagent itself. So for the mechanism, let's look at. So this is the electrophile, and this particular, sorry, this carbon attack is there, and it would generate this particular molecule. Quite easy. How we can solve this, and so this is the right answer. And Michael addition, we all know the 1,4 addition reaction, so that should not be the case here. So these two I am going to discuss, quite new. So unregistered homologation and cicibamine amination reaction. So this is unregistered homologation reaction. So at first we need to know what is homologation. So just this is our starting material and this is the product we have got. So if we compare these two, just you can see one carbon atom is extra over here. So that's how we can homologate or make one carbon extra between the functional group and the alkyl moiety. So many time it is very much useful and we need to do the homologation. So it is one of the example for that, how we can increase one of the carbon atom between uh, the alkyl or this partner and one functional group, how we can insert one carbon atom. So for this case, that what we need to do at first, we can at first need to make an acid chloride. So with associate to an acid condition, the acid chloride is easily formed. Then this CH2N2, this is treated with this chlorocompound. So when it is treated like this, so CH2, so this is actually this kind of thing, right? So this attack is there and followed by chloride removal. So it should lead to RCO2 into. So this kind of thing. So double bond type is, you can just many resonance forms there and it is one of them. Nothing fancy about that. And when it is charged with Ag plus in catalytic amount, this thing would be converted to acid. So let's look at the mechanism. So here you can see this particular thing is there, and then just this thing will lead to this particular intermediate CH double bond N this thing, and then it is again the resonance form, just resonance. So this electron richness of this carbonatium you can see is quite high, and which is this is nothing but a enol or enolate, and CO minus and carbon double bond. So just enol. So now yeah, okay. So people are there. So this thing now when it is treated with Ag plus, what would be happening? It is just the Wolff rearrangement. So Wolff rearrangement would lead to formation of this isocyanate. So they have not shown here. Let me just write the mechanism. Here itself I can do actually. So from here I am showing. So again this particular rearrangement and removal of N2, and this is facilitated due to presence of this Ag plus. So when this R group migrates over here, it would be formation of this particular type thing, which is isocyanate, and here you can see this is actually the Wolff rearrangement thing, and which would lead to formation of this. Now this is a very reactive species, and H2O can easily attack this, which would lead to this molecule, which is nothing but acid. So that's how this, here you can see, due to this shift, this particular carbon is inserted between one functional group and one, and which is it is attached. So that's how this two bond breaks, and one carbon group attaches between them. So that's how homologation occurs. So not only acids, if we let's say in the reaction media we had amine or alcohol, so we can respectively make their esters or amides. So that's how the control is also there. So not only acid to acid, acid to homologated ester, homologated amides we can easily make. So this is untested homologation reaction condition. So now tizibamine amination reaction. So this is for this type of pyridine carbocycles. And this R group is not only over here, uh, beta para anywhere it can. So when it is reacted with NaNH2, a very much strong base in presence of ammonia and heating condition, at first this ammonia can attack this particular center, because you can see it is very much electrophilic, and this particular attack is feasible. So after this attack, uh, this particular proton elimination can be there, and from here just H2 elimination would lead to formation of this C double bond NH bond, and just then just tautomerization thing actually, which will lead to formation of this, and just so you can see this particular what we did in this particular thing, we just incorporated one amine group, this particular NH2, in the ortho position. So that's why it is amination, and according to the scientist name, it is given amine amination reaction. So this kind of simple reaction conditions are there, and we just need to know this kind of name reaction. So that's how we can easily solve problems. So for the seventh problem, so yeah, so all four I have discussed. So you can now easily think. So this would be for different cases, not for this one. So that's how the things. Now this particular, so this is a particular very interesting reaction actually. So here you can see one of the alkyne is there, and particular this reaction condition, what would be happening. So at first they are asking if just one reduction would be happening, means triple bond would be converted to double bond. So if H minus attacks there, so this would lead to this particular kind of thing. So then this would be the product. And the second thing they are asking, the two level of reduction, means this double bond is reduced to this. So and here they are asking if this would be trans geometry or cis geometry, is that thing they are asking. So for this kind of things, we all probably you all know. So not on this base H minus with potassium, it cannot do this particular it cannot react as nucleophile. So here what is the role of H minus? Just base. So if we need to do the H minus as nucleophile, what do we need? LH type things, NaPH4 type things, or pH3 THF, this kind of thing we would need it if we want to use H minus as nucleophile. So this is not the case over here. So it can only act as base, not as nucleophile. So let's say this to this, how we can convert. So here also this is very reactive. So normal H minus should not do. So if we treat this particular reaction with, let's say, sodium ammonium, then one this thing would be there, and due to trans-stabilization, means negative over here and dot over here. So due to this stabilization only, there would be this particular uh, stereochemistry, and protonation can lead to this. Then only this A can be formed. So with this condition, this cannot be formed, and how we can do that? So H2 and palladium charcoal. Very much high pressure would be needing for this hydrogenation reaction. Then only we can fully reduce this triple bond. And for this double bond thing, again you can use this particular condition. So we need some catalyst poison, which are uh, 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 so here we use probably BaSO4 and quinoline, this type of and this particular reaction condition, I think, to lower the reactivity of the palladium or act as catalytic poison. That's how we can selectively remain in double bond form, not fully reduced form. So for this kind of hydrogenation, as the hydrogens are approaching from the same side, so that's why this stereochemistry is formed for these cases. So all the things are not possible are with this particular reaction condition. So you can, with the just elimination of product, we can just say the thing with BT. But let's look at the mechanism. So actually it is an alkyne zipper reaction. One of the very interesting reaction. So here you can see it is sp, right? So that's why the hybridization of the carbon is very much its character of this is high. So that's why it is, you can consider it as acidic proton. And as I have said, this H minus acts as base over here, so one of the proton would be abstracted. So H minus cap abstract one of the proton like this, and H2 would be eliminated. So then this thing would be formed, and this is there 1,3 diamino propane. So propane ring and diamine, right? So this thing is there in H2 and H2. Now what would be happening? Let me write the protons. That would be easier to discuss the mechanism. So I am writing NH2 like this. So acidic proton, this, and it would lead to this type of alene type of system is formed. So here you can write it like this, right? NH3 plus, oh, not NH3 plus, so it is NH2, and here and other part is NH minus. So NH minus, now again same thing would be happening again. Yeah, so again we have acidic protons over here and very much strong base actually NH minus. So they, so this kind of actually zipping thing is there. That's how it got stabilized actually. And that's how the actually the remembering would travel from here to the reaction. That this thing would be there, which would need to move ahead one triple bond. So anyway, I have probably one slide for this. Yeah. So here it is. So I am not going to show write the full thing. So that's why it is there. So in the first step, you can see this alene type thing is generated. Now the acidic proton of the alene can be abstracted by the NH minus, and this oh, this taking is there, so that's why we are actually diverting things. So acidity of the alene proton is there, so that's the thing. So here this and this, so this is also acidic proton, so that's why this abstraction is there, and here again we are generating NH minus. So one side NH minus is becoming NH2, another side NH2 become NH minus. So that's how flipping thing is there. Negative transformed and neutralized. So that's how the three member thing travels. Sorry, the triple bond travels between the carbons. So after this step, first step here, don't be confused. So this. So here you can see one level shifting of triple bond is there. So from this carbon carbon to this carbon carbon it is shifted. Now again we have acidic protons. So next step level of same thing, acidic proton formation of allenes thing is there, and this. Now finally this NH minus would be neutralized by this acidic proton, which will generate this, and this would be easily quenched by H plus and formation of this terminal alkyne. So here you can see from branched alkyne in between it come all the way to ekdam terminal one, and become terminal alkyne. So that's how the zipping thing is there. So uh, just like your zippers, so it's there, and when we pull the things it become like this. So that's how it zips actually. And the you can just think of the chain, we pull it all over here. So that's why the name is there, the alkyne zipper reaction. So from one particular carbon carbon bond it completely shifts to that. And one thing is that for this thing always, from any branch species we would be generating the terminal alkyne, then only this reaction would stop. So not only these two carbon, let's say we have here many things like this, and it would if we do this particular treatment, it would be stopped when it would be in terminal position. So that's how the triple bond actually travels all the way to the terminal one. So one of the interesting reaction. So this particular reaction condition can do that, and the answer would be T. Now coming to the ninth problem. So this particular reaction condition, the ortho esters, we all I means previously I have many times discussed. This is Claisen type rearrangement. So 3 3. So for this we always generate gamma delta unsaturated carbonyl compound. Always it is there, so like that we can just confirm. So alpha beta gamma delta, so definitely one of the possibilities, alpha beta gamma delta, one of the possibility. So if you have any question, can ask. So some of you have raised your hands, I think. So in that way we can eliminate option D, and let's see the mechanism, then only we can confirm which product is. So this is our starting material, and yeah, go ahead. Oh, so there it was here, or oh, okay. Oh, oh, that's no issue actually. Assignments. Yeah, yeah, it's fine. No problem. Okay. Mhm. Yeah. So with this particular condition and H plus, at first the species that would be generating, it would be this kind of species can be generated as here one at first one methanol thing would be removing, and followed by isomerization thing would lead to this, and then just 3 and which would lead to formation of this particular compound. Okay, so it is first actually. Yeah, so after the 3 elimination, this can be achieved, I guess. Yeah. So after the particular this attack, this particular thing would be generated, and then elimination of one methanol group would now 3 3 we do. So particular this gamma delta saturated ester would be forming, and that's why right answer would be B. So anyway, quite easier problems, and for the next problem, so this is also a name reaction thing. I hope all of you know. So the is this particular helpful and Zielinski reaction. So where this PBr3 and Br2. So this is actually that. So Br2 and PBr3. So here without PBr3 we can in situ also generate this PBr3 also with this particular treatment of phosphorus and bromine. So when PBr3 is generated and we have an acid, so mm, at first what would be happening? So just just like normal PBr3 how it do its thing. So oxygen phosphorus what would be bond would be forming, followed by bromine minus attack, and opening of one phosphor oxide followed by two bromine, and this species can again react, and like that H3PO3 and this particular thing can be generated. So now when this particular COBr compound is generated, so you can just think of formation of one enol, and again when enol is formed, bromine is there. So this particular attack is very much possible, and that's how in the two position bromine can be incorporated, which is nothing but this compound, and with acids this thing can coexist. So like that only here you can see for the after the first reaction condition, the product that you would be generating is uh, this particular compound here, bromine and COBr. This should be generated after one, and here you can see dry methanol is there in excess amount. So that's why the methanol can react with this bromo compound. Here actually methanol can attack like this, and followed by removal of bromine minus or HBr. Here Br can be any stereochemistry, so ester thing can be formed like this. So just like ester formation is. So for the amino acids how we do actually. So let's say we have purine. So from here we want to make its ester. So how we do? So SOCl2 and the solvent is methanol. So in situ actually SOCl2 at first react with the acid, and acid chloride is formed, and as uh, the solvent itself is methanol, it can easily attack like this and make its ester. So the same thing is happening here, but here acid bromide is forming, which is converted to its ester in presence of methanol. So quite easy, the answer is C. Now for this case, so from here to starting material, target molecule. So which particular reaction condition would be mostly suitable? So hydroboration oxidation. So if we do hydroboration oxidation of this particular compound at first, what would be our product? Let's see. So this hydroboration oxidation terminal alcohol would be formed. So this after first step this, then aldol condensation. So no aldol condensation is possible over here, but let's see we oxidize it further one step and make it aldehyde. So this, so now methyl. Now if we do the aldol, you can see the maximum what we can achieve a 4-membered carbocycle, not 5-member, because 1, 2, 3, 4 only alpha proton is there, so that thing cannot only be achieved like this. So that's how we can easily eliminate that. So next is Walker oxidation followed by aldol condensation. So let's see. So Walker oxidation, I hope all of you know. So Walker oxidation is well known for its oxidation in between not terminal CHO it forms this particular compound. Quite selectively, oxidation can do that, and in presence of aldol reaction condition, let's say base, so enolate would be formed here, and then this attack. So this should definitely make this 5-member carbocycle. So this thing would be formed, and base is there. So here E1CB elimination would be there, and actually aldol condensation reaction would be happening, and which would lead to your alpha beta unsaturated carbonyl compound, and which is our target. So that's how you can do that, and the thing would be this. So these easily you can do that, but let's see the other things also. So dihydroxylation followed by candidate, quite thing actually. So dry hydroxyl compound we can make, let's say this. So after that Cannizzaro, just RCH would be one part would be acid, one would be alcohol. So this kind of formation of this alpha beta unsaturated thing would not be possible, and again hydroboration oxidation. At first it would generate CH2OH, and which would kill the this particular selectivity of forming this. So you can easily eliminate. So let's see. Yeah, so for Walker oxidation, why it oxidize this position selectively, let's have a quick look. So the Walker-Suzy oxidation condition is this, but palladium chloride catalytic amount, CuCl is required, and DMFH2. So at first, this particular palladium complex in presence of ligands is there, and it form the complexation with this olefin molecule. So when the coordination is there, it forms like this, and after this particular palladium and pi acid coordination, the H2O can attack particular this more stable carbocation center. You can just think of, because the thing will be carbocationic or cationic attack is there. That's why this selectivity came. So each attacks in the bridget or in the branch position, not the terminal. So when this happens, then just this is the intermediate, then hydride transfer lead to formation of our ketone, and in that way, after removal of HCl, the palladium species is regenerated, and this is our co-catalyst, how the palladium is converted to palladium 2. So we need to do a oxidation step over here. So that's where palladium 0 to palladium 2, right? So oxidation we need to do. So for that something need to be reduced. So what is reduced? CuCl2. Here you can see CuCl2 uh, 2 plus is reduced to copper chloride, so it is reduced and it is oxidized. So that's how we to continue the cycle we need a co-catalyst, which is copper chloride, which helps to for this particular oxidation. But for this for copper's oxidation, which how we can do that? So that's where the O2 oxygen flow should be there in the reaction media. So that's why O2 environment is needed. So for the reaction, how it is done? So let's say you have a RB like this, and here we have DMF, magnetic beads, palladium, copper, and your product all is there. So how we can maintain the oxygen flow? Because if we make this thing open air, oxygen is there but not enough to do this oxidation, or it can do, but the rate would be, or you would need a more reaction time. So that's why how we have a needle like this, and here we have oxygen bin. So that's how we bubble at first this particular reaction media. And here let's say we have a again needle, how the, so let's say air is there, so oxygen flow over here like this and air remove like this. So if we continue this process, the reaction will be, that's how we can make the reaction quite faster to make the oxygen readily available in the solvent. So that's how we do in the labs. And for the siloane condensation, let's look at. So yeah, so siloane condensation is actually forming an ester to this alpha hydroxy molecule. So from here to here. So this is the particular condition for the siloane condition is there to do this transformation. So at first ester is there, and reagent is sodium. So sodium is you all know right now that it actually donates electron, single electron. So this particular thing is formed now. Two species of this are can recombine and make this particular CC bond. So when this particular CC bond is formed, O minus is there, and one O minus can remove the one of the OMEs. So good living group would generate this keto group over here, and in the same way OME, this OME also can remove and can generate this diketo system. But in the system we have sodium, so this thing cannot be can be survived. So again in the same way, two electron are donated like this, and reduction is there. So dot is formed, now double bond is formed. So this is particular ultimate fate of the reaction, but you all know this is just a, then protonation is there like this, and this is the tautomeric form of this particular compound. And why this particular tautomer is stable? Due to this internal hydrogen bond. So that's how a solvent condensation is there, very easy. And so I think for this case, yeah, so this is our today's last problem. So correct retrosynthetic pathway. So let's solve this. So they've given some particular options. So let's start. So this compound, if we treat with OH minus, right? So let's see. At first, what would be forming? Aldol condensation reaction first. So this thing would be formed at first, or CH also. So here it would be proton, not CH3. This thing would be formed. Now the second attack can be the alpha beta thing. So here it can attack. So if that attack is there, so we can only achieve uh, this kind of thing, right? And that's it, right? Uh, further further progress of this particular C3 CH2 system is not that much feasible. So this kind of species we would be generating if we only use this particular compound and base. Now let's look at the next condition. So for this combination, we can start like this. Here we have HCHO in the reaction media. So this attack should lead to formation of CH2OH, this thing. Now again it is an acidic proton, so 3 times or 2 more times same enolate formation would be there and followed by attack would be there. So if that thing continues, the product can be generated is this. Now very much basic medium is there, no alpha proton is there in this particular compound, so Kenny zero is possible. So Kenny zero, let me give you a quick mechanism. So is minus can attack like this, O minus this thing RCH is there, and always remember no alpha proton should be there. So this thing abstract this acidic proton OH minus there. So now what can happen, this particular hydride can be eliminated and attack this. So now it generates acid group, and here it is reduced, so CH2 is, so that's how thing can be. And so here in the same way we would be generating all alcohols, and another thing we would generate 3 alcohol and 1 acid. So with this particular condition we can achieve this particular all these things. So that's how answer would be B. And that's all for today's class, I think. So A can, and these are easy things, and you can easily correlate one how the all uh, 4 hydroxy thing can be generated like this. So that's all for today's class. Thank you for joining, and so Sunil Negi, you have raised your hand. So if you have any question, you can ask. Other people left. Other people left. Okay. So seems like no question today. Any questions? Further questions? So okay. So if there are no more questions, we can conclude, and this should be uploaded to YouTube there. If you have any comment or suggestion, and if face any problem, so there you can just comment. And one more thing is the feedback thing is there, so there please feel free to write and give rating. And so that's all for today, and thank you for joining. And we are almost uh, into towards our this course. Today is the ninth live session, so there will be, I think, three more live session would be there, and the time would be same, actually 6 to 8. So thank you for joining, and we will be meeting in the next Tuesday same time.